Hello everyone. Today I will be discussing my approach to improving the performance of my classifier and accessing its feed. Throughout this process, I implemented several techniques, including data pre-processing, feature engineering, class balancing, and hyperparameter tuning, and model evaluation. These optimizations were all aimed at enhancing the classifier's ability to make accurate predictions, especially in the context where the dataset posed several challenges. One of the major challenges I faced was dealing with an imbalanced dataset, where the minority class has significantly fewer samples compared to the majority class. This balance can often lead to biased models that tend to predict the majority class more accurately, while underperforming on the minority class. To address this, I applied SMOTE, which is synthetic minority oversampling technique, with a sampling technique strategy of zero point 0.6, meaning that the minority class was resembled to 60% of majority class. This technique generates synthetic samples to balance the dataset, allowing the model to better learn the patterns of the minority class. Additionally, I adjust the k-neighbors parameter to 3 to avoid excessive duplication of minority samples, ensuring a more diverse and realistic resembling process. As a result, this approach significantly improved the recall of the classifier, enabling it to better detect positive cases, which is crucial for the particular application. To improve computational efficiency and reduce redundancy in the dataset, I also applied principal component analysis, which is PCA. PCA is a technique used to reduce the dimensionality of the data while returning as much variance as possible. In my case, I set n components equal to 0.995, meaning that PCA transformation returned 95% of variance in the dataset, while discarding the less important features. This not only helped reduce noise in the dataset, but also speed up the training process, allowing for quicker model iteration without sacrificing predictive performance. By applying PCA, I effectively streamlined the dataset, focusing on the most relevant features while eliminating less information ones. Next, to optimize ChargeBoost classifier, I employed Grid Search CV, which is a method to perform an exhaustive search over a specified parameter grid to find the best combination of hyperparameters. The hyperparameters I focused on were max dips, which controls the dips of each tree, learning rate, which determines the step size for optimization, and an estimator, the number of trees in the model. The parameter grid I used, including values of max dip, 357, learning rate, point, 0.01, 0.05, point 0.1, and an estimators, 50, 100, and 200. By testing different combination of this parameter, Grid Search CV systematically identify the best combination, which ultimately lead to improvements in both precision and recall. This fine-tuning allows the model to better fit the data and make more accurate predictions. For model selection, I trained multiple classifiers including random forest classifier, ChargeBoost classifier, and LGB-MCI classifier to determine which one would best suit my needs. I evaluate the model based on their F1 scores, which provide a balance between precision and recall. After careful comparison, ChargeBoost emerged as the best choice due to superior performance, particularly in terms of achieving the best balance between precision and recall. ChargeBoost performance surpassed that of the other models, making it final model I select for submission. To ensure the model generalized well to new ANSI data, I implemented tenfold stratified into 10 equal parts. Ensure that each fold maintains the same class distribution as the original dataset. This helps to prevent overfitting by ensuring the model is tested on a variety of different data subsets. The cross-validation F1 score was 0.92, which indicate that the model was performing consistently across different subsets of the data, and it was not overfitting. This validation process provided a confidence that the model could generalize well to new data. Finally, after training the ChatGPT model, I performed a feature important analysis to the understanding which feature contributes the most to the model prediction. ChatGPT provide a built-in method to rank feature based on their contribution to the model's performance. By identifying the top 10 important features, I was able to gain valuable insights into the dataset and focus on the most relevant feature. This not only improved the model interpretability, but also guided my decision regarding future feature selection and potential data improvement. In summary, I improved my classifier by addressing class imbalance with SMOTE, applying PCA for feature reduction, fine-tuning hyperparameters with grid search CV, and carefully selecting the best model. To access model feed, I use cross-validation, adjust the classification threshold. The performed feature imbalance analysis. This optimization leads to a more robust and reliable classifier, capable of delivering more accurate and meaningful results. Thank you for your time, and this is all I can tell you guys.